Hello class. In the last video we ended just about here. So on the right hand side, what we have is a thermometer. Now it has two different temperature scales. It has temperature in degrees Celsius, and it also has temperature scale in degrees Fahrenheit. So it's possible for us to use this clinical thermometer to measure temperatures in these two different scales. Now I think here we just want to talk about the various boiling points and the freezing points of these three different temperature scales, and want to look at kind of like a backstory of how these scales came about. So you can see that in the early 1700s we had Anders Celsius. He is the one who came out with the Celsius scale. It was actually named after him because of the work he did. And we see that if we are considering the Celsius scale, the freezing point for water, it's 0 degrees Celsius, and the boiling point is 100 degrees Celsius. Now the freezing point is basically the point at which water, which is liquid, changes into a solid, and the boiling point is that point at which water, which is a liquid, changes into gas, into the gaseous phase. So we have the freezing point 0 degrees Celsius, boiling point 100 degrees Celsius. And now for Fahrenheit, it was named after G.D. Fahrenheit. So according to the Fahrenheit scale, the freezing point will be 32 degrees Fahrenheit, and the boiling point will be 212 degrees Fahrenheit. And also the Kelvin scale, which was also named after Lord Kelvin in the early 1800s. For the Kelvin scale, the freezing point is 273 Kelvin. And then while the boiling point for water is 373 degrees Kelvin. And here it's a point just to know that absolute zero, which I'm going to explain in the next slide, is actually minus 273 degrees Celsius. And it's mostly used, we mostly use Kelvin when we're talking about absolute zero, rather than any other scale, any other temperature scale. Now let's just answer this few questions, this one question, then we move forward. Now there is twice as much molecular kinetic energy in 2 tires of boiling water as in 1 liter of boiling water, which will be the same for both. There is twice as much molecular kinetic energy. So we're talking about the molecular kinetic energy. The answer just popped up. Anyway, we're talking about molecular kinetic energy. Now, kinetic energy, what does kinetic energy measure? Remember, when we're talking about temperature, we said that the temperature generally is a measure of the average kinetic energy at which those bonds are moving. They may be translating if it's in the case of a gas, they may be rotating if it's a case of a liquid, or they may be vibrating if it's in the case of a solid. And we said that if we can measure the average kinetic energy that these particles are vibrating, translating, or rotating, we're able to get the temperature of that particular substance. So if there is twice as much molecular kinetic energy in 2 liters of boiling water and 1 liter of boiling water, and as in which will be the same. So what will be the same? Is it the temperature? Is the temperature going to change? Is the thermal energy going to be the same? Will they be both? What's the case going to be? Now we discover that which will be the same. The temperature is going to be the same. Now it's funny, right? And the explanation is very clear. You see, the average kinetic energy of the molecules is the same, which means that temperature is the same for both. So whatever the case, twice as much molecular kinetic energy, but though we're talking about twice as much kinetic energy, we notice that the average kinetic energy, if it's in a solid, it's going to be the same because it's solid. But if it's in a liquid, if we're comparing maybe two different states of matter, for example a solid and a liquid, then we're going to see that the average kinetic energy for the liquid will be higher than that for the solid, and therefore we expect the temperature to change, to be different. If we're considering a solid and a gas, then we also see that the kinetic energy for the gas will be higher than that for the solid, and therefore the temperature will change. But if we are considering the same phase, like it's the same boiling water, no matter what, the average kinetic energy is gonna be the same because it's the same phase, and therefore temperature will be the same for both cases. Whether it's twice as much molecular energy, it's still 2 liters of boiling water, it's still boiling water, and the answer remains the same for this case. So absolute value, let me try to explain absolute 0K. So we already explained that temperature is the measure of the average kinetic energy or the average speed of the particles in a particular substance, and absolute zero temperature. Therefore, what happens is that it's possible for us to keep decreasing the speed at which those particles in the substance are moving. We can keep decreasing. If you look at the graph, we can keep decreasing the speed. We can keep decreasing the speed, and it's going to get to a point where these particles, they don't longer vibrate. What we're trying to say, at that point, there is no translational motion, there is no vibrational motion, there is no rotational motion between these particles. Now, when we get to that point where there is no motion generally, then we say that we are at absolute zero temperature. And at that point, the pressure is totally zero. And it's been discovered that at that point where no motion of there is no motion or no vibration in the particles, it's actually at minus 273.15 degrees Celsius. That's where absolute 0 degree temperature of, and this temperature, like it said, it's where there is no kinetic energy. The particles are not able to move. And at that point, it's not possible for the particle to get any colder. In fact, that's the coldest point at which a particle can be, at absolute zero temperature. So absolute zero or 0 Kelvin is the lowest limit of temperature. So it's either minus 273 degrees. So it's either this 273 degrees Celsius, or it's the same as 0 Kelvin. 0 Kelvin. So atoms or molecules have lost all available kinetic energy, like I said, and substance at this temperature cannot get any colder. So we have a case here, absolute zero temperature. When we want to look at an example, compare that to gas. The pressure of this gas generally is due to multiple collisions, as we already explained when we're doing fluid mechanics. So if we keep decreasing the temperature of the gas, it means that the average speed of the molecules also will keep reducing, and it's going to keep getting smaller and smaller. And because it's getting smaller and smaller, the pressure also is decreasing. So it gets to a point where the molecules are practically motionless. They cannot be able to move. At that point, we are at absolute zero, and at that point, the pressure of the substance is also zero. And I think we're done with this lecture, so we're going to continue in the next slide. So stay tuned and watch for